Welcome back to the deep dive. You're here, I imagine, because you want to get a handle on data analysis, but maybe without getting totally overwhelmed.
Yeah, keep it clear.
Exactly. So today we're looking at simple linear regression, basically drawing the best straight line through your data
A
points.
most informative line, hopefully.
Right. We're working from some foundational material, our pasted text source, and the mission is pretty simple. Get a really solid grasp of how this works, the core ideas.
Okay, let's do it. So, simple linear regression. It's about finding a relationship between two variables, right? One you want to predict and one you think affects it.
Like sales based on ad spend, maybe?
Perfect example.
Yeah.
But before we even draw that line, there are these key assumptions we have to think about.
Okay. What are they?
Well, first, you're assuming the underlying relationship is actually a straight line. It seems obvious, but,
Not always true.
not always. Then the errors, how far off our predictions are, they need to be independent. One error shouldn't predict the next,
Makes sense.
and their spread should be consistent. Think like shots scattered evenly around a target, not fanning out.
Okay. Constant variance.
Yep. And ideally, those errors should follow a nice bell curve, a normal distribution. If these assumptions are way off, our nice straight line might, well, lead us astray.
Got it. So, assuming the data behaves, how do we find that best line? The source mentions least squares.
Ah, these squares. It's actually a pretty neat idea. Imagine drawing any line through the data.
Okay.
For each actual data point, there's a vertical distance to that line, right? That's the miss or the error.
Residual.
Exactly. Least squares says square every single one of those misses,
Yeah.
add them all up, and then find the one line that makes that total sum as small as possible.
Minimize the squared errors.
You got it. And that specific line gives us our two key numbers, the slope and the intercept.
Right. Slope and intercept. So, what do they mean in practice?
Okay, the slope.
Right.
That tells you how much you expect your target variable, your dependent variable, to change when your predictor, the independent one, goes up by 1 unit.
Like, for every extra hour studied, the score goes up by this much.
Precisely. That's the slope. The intercept is, well, theoretically, it's the predicted value when your independent variable is 0.
Sometimes that makes sense. Sometimes, maybe not.
Exactly. Like predicting weight when height is 0 doesn't make sense. But predicting sales with 0 ad spend, that could be your baseline. So context matters for the intercept.
Okay, so we have the line. How good is it, though? How well does it fit the dots? That's R squared.
Yeah, R squared, the coefficient of determination. It gives you a percentage, basically. It tells you what proportion of the variability in your dependent variable is explained or predicted by the independent variable using your line.
So an R squared of 0.6 means 60% of the variation is accounted for.
Yep. 60% of the ups and downs in your outcome variable seem to track with the ups and downs in your predictor variable. It's a measure of fit. But be careful.
Uh-oh.
A high R squared doesn't automatically mean it's a good model or that X causes Y, just that there's a linear association captured by the model.
Good point. The source also talks about the standard error of the slope. Sounds important.
It is. It's about reliability. If you took different samples of data and calculated the slope each time, how much would those slopes jump around?
Ah, so the variability of the slope estimate itself.
Exactly. A smaller standard error means you're more confident that the slope you calculated from your sample is close to the true slope for the whole population. It's crucial for testing if the slope is statistically significant.
Okay. And what if those errors, the residuals, aren't bell-shaped? What if they're skewed or something?
Well, if the errors aren't normally distributed, it messes mostly with the statistical tests. Like our p-values and confidence intervals might not be quite accurate, especially if the sample size is small. The line itself might still be okay as a description, but the inference gets shaky.
So checking the fit, it's more than just R squared. We need to look at those residuals.
Absolutely. You plot them, you look for patterns. If they look like random scatter around 0, that's good. If you see a curve or like a megaphone shape where they spread out,
A pattern.
yeah, a pattern in the residuals means your simple linear model is probably missing something. The relationship might not be linear or the variance isn't constant.
Got it. And how do we formally test if the slope isn't just 0? Like, is there really a relationship?
Right, that's hypothesis testing. The null hypothesis is usually that the true slope is 0, meaning no linear relationship. We calculate a test statistic.
Usually a p statistic.
Often, yes, especially with smaller samples. We use the t-distribution to figure out the probability, the p-value, of seeing a slope as steep as ours or steeper if the true slope really was 0.
And a small p-value means...
It means it's unlikely we'd see such a result just by chance if there were no real relationship. So we reject the idea that the slope is zero and conclude there is a statistically significant linear relationship.
Why the t-distribution specifically? Why not the normal z-distribution?
Good question. It's because we usually don't know the true standard deviation of the errors in the population. We have to estimate it from our sample. This adds extra uncertainty, especially with small samples. The t-distribution has fatter tails than the normal distribution to account for that extra uncertainty.
Makes sense. More cautious.
A bit, yeah. It leads to slightly wider confidence intervals and makes it a bit harder to reject the null hypothesis, which is appropriate when you have less data.
Okay, nearly there. Outliers and leverage points. What's the quick story on those?
Okay, so outliers are points that are far away vertically from the general trend of your line. They have large residuals.
They don't fit the pattern.
Right. Leverage points are points that have extreme values on the independent variable way out on the left or right of your scatter plot. Both can be problematic. An outlier can pull the line towards it. A high leverage point can pull the line dramatically if it's also an outlier, or it can sometimes anchor the line strongly even if it fits the pattern. You need to identify them and see if they're like data entry errors or genuine interesting data points.
So, lots to consider. Let's try and quickly sum up simple linear regression. It draws a line.
Assuming linearity, independence, constant variance, normality.
Right. Assumes those things. We find the line using least squares to minimize errors.
And the slope and intercept tell us about that relationship.
R squared gives a sense of fit. Standard error tells us about slope reliability.
Check the residuals for patterns. Test the slope using the t-distribution.
And watch out for those outliers and high leverage points.
You got it. And, the really important thing is that these core ideas, they don't just disappear. They pop up again and again in more complex models.
So understanding the assumptions is critical before you believe the output.
Absolutely critical. Always ask, does this model, do these assumptions actually make sense for this specific problem, for this data?
That's a great point to end on. And hey, if things like checking residuals or dealing with outliers caught your attention, definitely explore those topics further. There's always more to learn. Thanks for joining this deep dive.